I am so glad you convinced me that the family car should be the Defender 110. It is so beautiful inside, it's so comfortable, and it just feels indestructible.
Yes, it really is. I've been waiting a long time for the new model to come out. The Defender 110, I'm telling you, it's my favorite car of all times. It's my third one. You know, I have stories of going off-road. The guy managed the group. He was like, what are you doing in this beautiful car? I'm like, I'm going off-road. He's like, are you sure? Because you can use one of ours. And then they look like Mad Max cars. I'm like, no, we're going to do this. And he was shocked.
Wow. Well, it's great because the Defender has been reimagined for 21st century adventure, and its unparalleled off-road ability as well as its robust interior are invaluable whether you're headed towards uncharted territory or just a weekend of exploration. The Defender 110 tackles challenging surroundings with absolute confidence. The SUV conveys strength outside and in, featuring peerless technology like an intuitive driver display and an award-winning infotainment system. That's my favorite part, to keep you connected no matter where the journey takes you. Adventure is unique to everyone, and so is the Defender. Choose from the two-door Defender 90, the four-door Defender 110, or the larger Defender 130 with the ability to seat up to 8 passengers. You'll find uncompromising performance in all three. So pack up and go even further with the Defender 110. Learn more at LandRoverUSA.com/Defender.
These days, we're all investors, trying to be smart with our money despite our worst impulses. But at iShares, we believe that deep down inside of every investor is a better investor. One that's just waiting to be let out. Explore iShares ETFs and insights and let your best investor out. Visit iShares.com for more information.
This isn't your average business podcast, and he's not your average host. This is the James Altucher Show.
All right, so once again, almost Nobel laureate in physics, Brian Keating. Brian, welcome back to the show.
James, it's always a pleasure to be back with you.
And so this one, I reached out to you, and I really wanted to understand something and explore this one idea with you, and you're literally the best person on the planet to explore this idea with. This is what you research, what you've spent your life on, the beginning of the universe. So I don't want to just talk about the Big Bang, which is the common theory of the beginning of the universe, which we'll discuss, of course, a little bit, and we've discussed on our other podcasts. But there's like other theories of the beginning of the universe, and I want to discuss them, learn about them, learn how people are exploring them, or whether they're just kind of science fiction. You know, it seems like some of these theories, it's like, oh, you could just sit around and make it up, like, oh, we're a ninth dimensional needle in some other dimensional guy's pocket and it fell onto the ground and then the Big Bang happened. Like, I could come up with any science fiction thing. And so I want to sort of understand what seems to be real science and what's just theory. And I just love this stuff. I want to know all the theories. So we're gonna cover everything from the Big Bang to VR simulations and everything in between.
Absolutely.
And just to cover, your research is basically, you're trying to pierce the veil of the cosmic background radiation that started to appear about 380,000 years after the Big Bang. And it's so thick, we've never been able to look past it to see the actual potential Big Bang. It's like this mystery that it's almost like God cloaked the Big Bang for us with this cosmic background radiation. But your insights were, and others as well, and you built this telescope to see gravitational waves that could get through cosmic background radiation. And just out of curiosity, what's the current state of that?
So we're building a series of different experiments that investigate these mysterious forms of radiation. We call it radiation, but it's not like some nuclear blast or something. Anything that propagates at the speed of light can be considered radiation. So it could be even things that have mass that propagate close to the speed of light, like a neutrino or something like that. You might consider that radiation. It just depends on how old, how hot, how dense the universe is, what you consider these things. But light obviously is the most common form of radiation. But there's other kinds, and one of them is what's called gravitational radiation, or sometimes called gravity waves or gravitational waves. And these are disturbances in the force. These are fluctuations in the fabric of every possible event in what's called space-time. So Einstein taught us to think of space and time not as separate, disparate entities, but actually as this fabric woven together in 4 dimensions. And that's the 4th dimensional aspect of it is what makes things so difficult for the human mind to comprehend. And in fact, lurking within the mathematics, what's really cool about relativity, general relativity, and you know this from your advanced class that you took with me, everything I needed to know I learned in kindergarten, that subject is so beautiful because it has math, and the math almost forces you by its structure to come up with certain conclusions, and those conclusions are in the form of equations. And they're so baffling but so unavoidable that Einstein didn't even believe that one of the implications was that the universe might and should have perhaps had a beginning. And that's what we're here to talk about today. Did it have a beginning? It's not mandatory that it had a beginning. It could have had multiple beginnings. And all these things really can be not proven. That's the first misconception I want to get out of the way, is that we'll probably never be able to prove how this happened, how the universe, how our observable universe came into being. But we can exclude a series of alternatives that we're going to talk about today, 10 alternatives to the Big Bang. And those alternatives, in some sense, could have been king, could have been right, but they were displaced or will be displaced, or maybe they won't be displaced, in which case the Big Bang would get displaced. That's what's so exciting. I call experimentalists like me building these experiments all around the world kind of like exterminators, because just like with termites there and cockroaches in New York City, where we're both from, when you step on one and you kill one, there's always more left. But your job is really as an experimentalist to exterminate as many theories that could have been true but aren't.
So, since we've never been able to see, well, okay, I'm going to get to the Big Bang in a second. First, there was the theory before that, which is this idea of a steady state theory, that the universe has always been here. It's always been the exact same size, and it appears to be expanding because every now and then pockets of matter are created, which is the part of this I don't understand. But I guess I grew up thinking, I didn't think necessarily the Big Bang. I kind of, as a kid, remember thinking, oh, the universe has been here for infinity and is just infinitely big. So I remember even my grandfather telling me, if the universe has an end, what's on the other side of that end?
Yeah.
And so I thought, okay, that he just proved infinity. He blew my mind. I was 6 years old, and he blew my mind with that. Right. But what the steady state theory, that kind of seems on the surface wrong, just because how does matter get created?
Yeah, so we skipped a couple of models before we even got started. But let me say this. For thousands of years, people thought just like you and your grandfather. It seemed natural that the universe was eternal because the human mind is kind of averse to thinking about things arising from nothing, if indeed such a thing could have happened and maybe did happen, as we'll get to. And so the dominant paradigm, as we say in science, we go from paradigm to paradigm, and the paradigms are usually overthrown by the advances in technology. But what's very interesting about the conjecture that the universe is eternal is that the only technology that one needs to falsify, which is what all we can do as scientists, we can't prove stuff, we can prove stuff wrong, we can't prove stuff right, is the technology that you need to falsify the eternal universe human beings have had for millions of years. Literally, they're just our eyes. And the way to think about this is, even in New York City, even in Florida, even in California, wherever we may be listening to this, the night sky is dark. And that's kind of unusual, right? Because you think about it for a second. Imagine the universe is not populated with stars. Imagine for a second you're inside of an infinitely old, infinite forest with beautiful trees growing up in all directions. And everywhere you look, you see the bark of a tree. You see the trunk of a tree. And no matter where your line of sight terminates, no matter where you look, it looks like you're surrounded by a uniform tree, an average tree. And that tree paradox was something that was later called Olber's paradox, which was that the night sky is dark, which none of us need a telescope to verify, other than the 2 telescopes in our eyes, which are little tiny refracting telescopes called our eyeballs. And those tell us at night the sky is dark. What does that mean? That means if the universe is filled with some number of stars per unit area, so anywhere you look, there'd be a star, then if the universe is infinitely old or infinitely big, it has an infinite number of stars. And those stars, no matter where you look, should be where your line of sight ends.
Our eyes are only so strong, right? So I can't read a book that's a mile away, even if I could see a mile distance.
Right.
So it could be the case that some stars just are, a billion light years away. So I'm not going to be able to, they'll look dark to me because it's like a needle, smaller than the smallest needle point.
Yeah, but the light doesn't change its intensity just by traveling. Light is kind of a perpetual motion machine. So if you shoot a laser beam from here to a billion light years away, that laser beam will arrive, modulo the fact we now know the universe is expanding, but forget about that. It will arrive with essentially the exact same intensity, the exact same properties that it had when it left.
Doesn't it spread out? Like, look, a camera light can't light up a stadium.
No, but imagine again, you're in this forest. So you may say, well, there's not a tree everywhere I look that's the same distance away from me. There's a tree 6 feet away from me. There's a different tree 7 feet away from me. But there's an infinite number of trees. This forest is infinitely big. It's infinitely old. There's plenty of time for light from the farthest reaches of the forest to get to your eyes. No matter where you look, it's unavoidable. You'll see a tree. And so even though the stars are very small, and even though some of them are quite far away and light takes a long time to get here, infinity, as Woody Allen said, eternity is a pretty long time, especially towards the end. And in this case, looking out in all directions, your eyes would end up on a star. Now, you look at those stars, they're pretty small, right? It doesn't like, oh, my eyes are blinded by it. But if there's an infinite number of these tiny little infinitesimal beams of light, then the light that you'll see in all directions, it's like you're surrounded by this glowing ball, a sphere of light, a shell of light. Each dot is as bright as the surface of the sun.
I see, because there's a essentially infinite or unimaginably high number of stars that even if they're tiny pinpoints and any one of them I can't see, all of them together, I should actually just see this completely uniform wall of light.
Just like you'd see the average tree in the forest that we talked about earlier, you'd see the average star, which is kind of like our sun. So actually, the night, there should be no darkness. If, again, this is a paradox, and like most paradoxes, Zeno's paradox, the famous one, it has resolutions to it. In this case, the resolution has to be that one of my assumptions is wrong. Either there's not an infinite number of stars, or the universe isn't infinitely old. So there may be not enough time for light to get to our eyes from distant regions of the universe where these stars had light that set off towards us.
But there is a third one, which is that there could be an infinite number of stars further than, but if it's infinitely old,
yes.
So I was thinking further than the 13.8 billion light years that we would be able to see, because that's how old the universe is.
Exactly.
But we can't see some of them because of expansion,
Right.
which we'll get to later. But
that falsifies the paradox. Exactly right. So exactly the way that this paradox can be resolved, and this could have been realized, or it could have been realized to either falsify the steady state or to at least alert scientists, astronomers, to another possibility that the universe might not be static. Remember, I said static means that it's not expanding. It doesn't mean it's contracting. It doesn't mean it's expanding. It just means that it's stationary. And one of the options that we'll get into, and maybe it's a natural time to get into it, was really considered in the 1600s, and it was related to the fact that basically a claim that was upheld even to the time of Einstein was that the universe was infinitely old. It wasn't expanding. It wasn't contracting. And this universe came to be called the static universe. That was not permissible, as I discuss in my book, because physicists realized when they observed Edwin Hubble observed that galaxies were in motion, that they were unavoidably moving away from or towards the Milky Way galaxy, or the Earth, if you like. And so that falsified the claim that the universe was static. It didn't mean that the universe was infinitely old or finite in age. So that at least ushered in the notion that the static universe, which is one where nothing changes on average, that the galaxies are not in motion, that was falsified. That was dead as of the 1929 period when Hubble first observed these galaxies receding away from us.
And just to explain it almost, or to ask, it almost works like a Doppler effect. So when an ambulance is coming towards me, it sounds one way, and when it's going away from me, it sounds a different way, even though it's the exact same sound. So a galaxy or a star moving towards us works, light waves work like sound waves. It's going to have a different color on the spectrum than if it's going further away from us, even though the color of the star itself is the same.
Right. So even if you heard every ambulance in New York City and they all had the exact same pitch frequency, then you'd know that they're all at rest relative to you. Now, if you hear them all getting redshifted or lowered in frequency in the Doppler shift, wah, 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 like that, then you know that they're all rushing away from you and you were probably at the scene of an accident and they all picked up the bodies but yours. Similarly, if you heard them increasing in frequency, wah, 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 like that, they're all coming towards you. And so, yes, the analog occurs, the exact same phenomenon occurs with light, and that's called redshift blue shift. But what Hubble showed and his collaborators was that with the exception of a handful, literally a handful of galaxies, every other galaxy in the universe, now we know there's over 100 billion galaxies, all but 6 to 10 of them are moving away from us. Not the 6 to 10 million, not 6 to 10 billion, 6 to 10, that are very close to us, that are actually being gravitationally pulled towards us.
So that's called the local cluster. That's our local cluster of
galaxies. Yes, we have a local cluster of galaxies, exactly. And then there are clusters of clusters called superclusters, and there's even mega supercluster. We're not going to get into that necessarily, but suffice it to say that for the purposes of the static universe, it could not be maintained anymore. And nobody believes in the static universe outside of a couple of crackpots who happen to have my email address for some reason. But that's another.
Do they really? Do you get emails?
I get emails. Yeah, once every couple of days, I'll get an email about the state of the universe or how it was created. We're going to get into some real doozies, later on as we proceed through the 10 different ways the universe could have started. And some of them, are familiar to me from these emails that I get, usually attached with the phrase, Professor Keating, I've got this idea, and if I'm right, which I know I'm right, but if you help me, I'll share some of my Nobel Prize winnings with you. And I say,
that's very nice of them.
Yeah, I said, well, I don't think you want the guy who wrote Losing the Nobel Prize as your collaborator. And that's the way I gracefully exit from that problem. But what was so interesting to me is even after the static universe was, and this happened in sort of the 1800s, actually Edgar Allan Poe had one of the first kind of correct solutions to the outcome of Olber's paradox that we just discussed, namely that the universe can't simultaneously be infinitely old, full of infinite number of stars, and not expanding or contracting. So Poe actually had it.
On that point, I want to ask you, so two things. One is, we talked about you have to have all the math and all the 20 years of calculus to be able to have legit theories in particularly this kind of physics, which, as you mentioned, can't even really be proven anyway. It all has to start with a thought experiment anyway. This paradox wasn't figured out by math. It was figured out by logical reasoning. Einstein came up with relativity after he thought about what would it be like, someone on space versus someone riding on a ray of light or whatever. Mm-hmm. So here, Edgar Allan Poe obviously didn't know all the math of theoretical physics and whatever, but he was able to come up with a solution that people listened to.
And so is your grandfather, right? Because, if you think about it, you go to the edge of the observable, or the edge of the universe and throw a spear, as the ancient Greeks used to say thousands of years ago. They didn't know, basic things in geometry prior to Euclid. And they had these same kinds of thought experiments. And it's funny that you say that, because I actually do believe Albert Einstein, who's mainly known for his theories of relativity, and we should actually say, what is a theory? What does it mean in the context of physics? But Albert Einstein is perhaps the greatest experimentalist, exactly for the reason that you say. He did Gedanken experiments. I love German. Don't you love German? They have great, my favorite word in German, we were just talking about ambulances. Do you know the word for ambulance in German?
No.
Krankenwagen. It's a Krankenwagen. Please
have to use that in daily conversation.
Yes, exactly. Yeah.
Wait, what's Gedanken?
Gedanken means thought. Gedanken experiment. So it's a thought experiment. And what he would do is contemplate, if I was traveling along a light beam, what would I see if I looked in the mirror? If I was in an elevator going up near the surface of the Earth or deep in space, could I distinguish between the acceleration in an enclosed elevator or being on a rocket? In other words, is acceleration equivalent to a gravitational field? What was so interesting about what Einstein did, even in the wake of Olber's paradox being present, he didn't give up the notion that the universe could be static, even though it was an outcome of his famous equations known as general relativity. There's two forms. One is called special relativity. It should be called specific relativity, right? But the other one's general relativity. And that's the theory of how gravity behaves based on just one simple ingredient. All you have to do is one simple trick, and that's specify how matter is in the universe. So think about it for a second. You ever thrown a ball up into the air? You're throwing it with your girls, and you throw a ball to them, and it comes down, right? But why does it come down? Why does it come
down?
Gravity. So what's causing gravity?
Well, the mass of the Earth.
Yeah, the mass of the Earth is pulling on the ball, and it's pulling it towards her. Now, the Earth is one, but of a tiny number, tiny fraction of the amount of mass in the observable universe, even according to Einstein, right? So there's some stars over there. There's some galaxies over there. Maybe he didn't really believe that they were galaxies until the late 1920s, but nevertheless, he knew about stars, right? So they thought stars were fixed, and actually he forced his equations to require no motion in the universe. Humanity's greatest mind. Now, what's wrong with why is that logically inconsistent, or what's wrong with that?
Well, I guess because, for instance, we know the Earth moves around the sun. We know that everything somewhat close to us, we have some gravitational pull over it, even if it's so tiny it can't be measured.
Exactly.
So that means every star in the universe must have some, at least tiny, infinitesimally small effect on every other piece of matter in the universe.
Right. And so it must pull it towards some central conglomeration of matter, like the Earth's
Unless
center.
everything's totally uniform. So there's like somehow, I don't know.
But he didn't believe that, because that was after Olbers, right? So 50 to 80 years after Olbers' paradox was sort of resolved, that the night sky isn't infinitely dark, the conclusion that people would say is, well, the universe isn't infinitely large, or it doesn't have an infinite amount of matter.
But wait, what was Edgar Allan Poe's solution?
I think he came up with the right idea, that one of those two assumptions of infinities, either infinite numbers of stars or infinite amount of matter, were incorrect. But it's very difficult to get everything in the universe to be isotropically distributed, right? To get perfect symmetry. And remember, if you break the symmetry by just a little bit, that's all it takes to get a tiny bit of force, the force of a ping pong ball, in your hand. That would eventually, over an infinite amount of time, be sufficient to cause all the matter in the universe to agglomerate together. So Einstein had to propose a counter form to the gravitational force. And exactly that is what he did. He put into his wonderfully beautiful equations this ugly term, later called the cosmological constant, or the vacuum energy, which he later called his biggest blunder. Nowadays, we know it was his biggest blunder to call it his biggest blunder. So even his biggest blunders lead to Nobel Prizes. But nevertheless, he put in basically an anti-gravitational force that kept things from falling together. And this was solved very differently by someone named Isaac Newton, who recognized the exact same paradox that you and I just discussed, that balls come down because of gravitational force. So Newton came up with the idea of universal gravitation, and yet he knew that things weren't all crashing into each other. And so he proposed, what do you think he proposed? So Einstein added a cosmological force into his equation. What do you think Newton added to his equations of gravity, or at least philosophically to them? Let me preface this by saying, do you know what Isaac Newton claimed was his best accomplishment in his life? He invented calculus, he invented gravity, optics, forms of mathematical optics. What do you think he claimed was his singular achievement in life?
I don't know.
That he died a virgin. Like he wanted to emulate Jesus Christ. He was incredibly religious. He was a very pious person. And so that's a hint. So he thought very highly of religion, which we'll get to eventually, I'm sure, as one of our cosmogonies, ways to describe how the universe began. But he believed that there were angels, essentially, like there were these forces, extrasensory forces, that kept things in place, so as not to distort the distant universe, would not come into collision with the local universe. So it's pretty interesting that these great intellects have these great, kind of blind spots, literally.
But that might not turn out to be a blind spot, and I don't mean that in a religious way. But there's other theories involving like dark matter and dark energy where those could take on the role of what he would call angels, not in a personal or fictional way.
No, that's
but like
what the cosmology exactly. And I like to say that. I have a video that's on the channel called Prager University, which I'm sure now half the audience is turning off the show. But I have a video, and the title of it's "What's a Bigger Leap of Faith, God or the Multiverse?" And in that we get into a very, very interesting prediction of one of the cosmogenesis laws. And I don't make a case for God. I'm not really in that game. I don't care what people believe personally. But the point is that there is sort of an element of faith that has to come with all scientific theories, whether people deny it or not. And actually, in the case of the multiverse, the actual creators of the theory of the multiverse say that it is basically an article of faith, but their faith is somehow guided scientifically more than, say, someone who's purely secular when it comes to these theories.
It's interesting because this goes into the area of not what theory is right, but how do you filter theories? So, I always have this belief that if too many things have to conspire to work together,
Conspiracy number.
yeah, the conspiracy, then it doesn't work. Then it's just a conspiracy it's not real. So like, a great example being 9/11, everybody says, oh, it was planned. They were all crisis actors, whatever. There would have to be thousands of people who were involved and who have magically kept their mouths shut for 20 years. So obviously it's not true.
Right.
And it seems like at some point, some of these theories there's a lot of evidence, like we'll talk about the Big Bang Theory and so on. Some of these things start to veer into, it might be true, nothing's really going against it. And then some things just seem to be like, okay, I'm just pulling a theory out of a hat with nothing to go either direction on it. It's just fiction.
Right.
So that's what I get nervous about with some of these ideas. And then, by the way, that might apply to the entire string theory aspect of physics. I don't really know.
Yeah, we actually had a big series of debates. So 100 years ago this year, in 1920, there were a series of debates held at the Smithsonian Institution in Washington, D.C., as to whether or not the Milky Way was a galaxy or not. So nowadays, we just take it for granted. We all have that screensaver on our Macs, right, with the galaxy. Don't ask how expensive that picture was to take of the Milky Way galaxy, because that is really a long shot. No, that's not the Milky Way galaxy. But anyway, it's not even a real galaxy. They actually, kind of constructed the.
I always thought it was like Andromeda.
It is. It's a version of Andromeda.
Or there's M1 something.
Yeah, it's M31, but it's actually enhanced and actually distorted. Anyway, but that was an open question. Was that object, and I'll put it in the illustration on my YouTube channel, kind of this great debate, whether these things that look like spiral swirls, I can show you a spiral swirl that is a couple of dozen light years away. It looks just like the Milky Way galaxy or another galaxy, the Whirlpool galaxy. And so it was a very good question whether or not those things were actually inside of our own galaxy. Don't forget, as late as the 1700s, people didn't know that comets were not like meteors, which were in the atmosphere. They thought comets were in the atmosphere. Actually, Galileo had a series of debates about this. Nowadays, we just take it for granted. Oh, Halley's Comet, it's floating around in space. You don't know much about it, but it's outside of the Earth for sure. But they didn't know back then that could just be like a meteor, which is actually in our atmosphere. A meteor caused a meteor shower. And what's so interesting to me is that, yes, you're right. When people do conjecture these things for which we have no direct evidence, it's very difficult to be an astronomer because we can't do experiments. I might have mentioned this last time, I don't remember, but if I'm a biologist, I think they play around with frogs a lot over there in the biology department. Actually, I think the dean should start an investigation. But
Yeah,
they
it's
take
like frog brutality.
Yeah, they take a frog, they expose it to UV light, they see, does it get a burn, they compare it to another one. Again, I don't know what the hell they do over there. But the point is they can do an actual experiment. They can see what happens when I change a variable and compare it to something I didn't do that to, double blind test, et cetera. And you could talk about whatever. Chemistry, you mix two chemicals together. You don't do that with another set of chemicals. But in astronomy, how do you do an experiment on a galaxy? How do you change the temperature of the sun and see, well, what does that do to the melting point of Earth's liquid oceans or ice or whatever? You can't do an experiment. So the only thing you have has to come to you across the universe and then be processed by our supercomputing brains and deciphered as if there was an experiment to be undertaken. So it's very challenging to do. So I'm never disparaging Newton or even the early, concepts of how cosmology could have evolved or how the universe could have evolved. It's very difficult to do what my colleagues and I do. And I'm not just saying that because I think it's the greatest thing. It is an accepted fact that we just cannot do an experiment. So how do you rule something out? I told you my job is to rule out theories, not to prove them in any way. So getting back to, these early theories, they knew the universe couldn't be infinitely old, infinitely big, and filled with infinite numbers of stars.
I have one more question about that one. And
Yeah.
I don't mean to spend so much time on the steady state version of the origin of the universe, but couldn't it be that, our solar system, our galaxy, our local cluster was just surrounded by a lot of micro dust, like, meteor-like dust that was just dark, had no energy.
Yeah, very
so
good.
ultimately, only a few stars could make their way through this dust that we could see.
That's very good. That's a very good point. So what happens is, no matter what you make, you cannot make something that, in your model, the Altucher dust would absorb the light, right? What happens if you put your hand out and you close your eyes? Can you detect the sun? I don't know. Are you in Florida right now? I forgot.
Yeah.
Yeah. So you go outside. Hopefully it's clear. It's not a thunderstorm yet. You hold your hands up. You close your eyes. You can locate the sun to within a few degrees on the sky just using your hand, right?
I guess so. I haven't been outside in like a few months, I think.
Your
but
complexion,
that's
I couldn't
probably
tell.
true.
I couldn't tell from your complexion and your pristine pajamas. But the point is that your hand is like that Altucher dust, right? It's blocking the light. What happens to your hand? It starts to heat up. Now, what happens if you leave it for an infinite amount of time and there's nothing else like the Earth's atmosphere or whatever? Eventually, your hand is going to come into what's called thermal equilibrium. It's going to come to the infinite temperature, the large temperature of the surface of the sun, which actually isn't infinite. The temperature of the sun is only, is only about 5,000 degrees Kelvin, roughly the same in Celsius. So it's not like it's infinite or, the core of the sun is much hotter, but the surface of the sun, which is all that's relevant here, would eventually heat up the dust to that exact same temperature because there's no way to be perfectly opaque. Anything that's perfectly opaque is perfectly absorbing. And so eventually that material will start to glow at the same temperature that the illuminating object is at, namely the surface of the sun.
There's no way it could have had just enough color to bounce the rays off back in the other direction.
Well, then it won't. So then it's slightly reflective, but there's nothing that's perfectly reflective. And given an infinite amount of time and the source of infinite amount of energy, it would eventually come to the same temperature as the illuminating source. That's called a black body. So that's a very important concept in physics that wasn't actually thought to be related to cosmology at all until we discovered this cosmic microwave background, which is the most perfect, uniform distribution of light that follows what's called a black body radiation curve. And what's so interesting is that all these theories of physics, of quantum mechanics, of what's called thermodynamics, those all came about during the same milieu of the late 1800s, early 1900s, Max Planck, Albert Einstein, Ludwig Boltzmann. They all started to have these ideas that maybe the quantum world and the macroscopic world, where we talk about temperatures and heat and entropy, maybe they were linked together. And maybe even the concept of time itself is linked to the properties of the universe itself. And that's actually one of the cosmologies that we'll talk about.
Oh my gosh, I love these clothes. Mizzen and Main. That's Mizzen and Main. It really is the most comfortable work clothes. Travel clothes. I had to travel this whole week. I'm traveling for a week and a half, and I just took Mizzen and Main clothes with me. Close out 2023 in style with comfortable, breathable, packable, and machine washable pieces from Mizzen and Main. As you wrap up your year-end goals, enjoy a Mizzen and Main dress shirt that you can wear confidently. I like that they've very, very just nice, solid colors. I don't really like to get all fancy in patterns and everything, although they do have some pattern shirts, but very comfortable clothes, stretchable pants. It's just super comfortable, but they look professional, and you can wear them casually or professionally. I like some of their flannel shirts or untuck shirts. I love untuck. I never tuck in. So again, whether you're shopping for a special someone or giving yourself the gift you really want, I just buy myself gifts. Mizzen and Main is the perfect gift for any guy who works, travels, and or cares about looking and feeling great. As you could tell by my many photos across the internet, I care about looking fantastic. I'm practically a model. And let's be honest, every guy loves to look great. So again, shop now at mizzenandmain.com and save 20% when you spend $130 or more using promo code James. That's promo code James at Mizzen and Main, Mizzen and Main.com. You know what I love about fantasy sports is that even though I'm not going to be a great basketball player or a baseball player or a football player or whatever, I feel like I get to participate and make decisions and use my knowledge of these different leagues or these different sports to compete. So it's like I can pick my team or I can pick my favorite players, and I could use my knowledge to make predictions and maybe even make money. So with the basketball season here, you can now pick combo projections across football and basketball from the Specials League on Prize Picks. This is a league created specifically for combo projections that include two or more players from different sports or leagues. Want to play alongside some of Prize Picks' favorite players like rapper Meek Mill and comedian Andrew Schultz, who's also been a guest on this podcast, and I've been a guest on his? You can now find community plays under the promos tab of the app to view entries for some of the biggest names in the Prize Picks community each week. Look, Prize Picks even offers a reboot policy so that your entries stay in play even if one of your players gets injured. For football and basketball games, if you have a player who exits the game in the first half and does not return in the second, that player is rebooted. Prize Picks is the only daily fantasy sports platform with an injury insurance policy. What? So I love playing it. I love anywhere where I can use analytical ability with my interests to demonstrate some skill and maybe make some money. And I like the game-like aspect. I do wish they had chess as a category on prizepicks.com, but I'll settle for what they've got. Maybe I should make my own fantasy chess league. But in any case, I love Prize Picks. Go to prizepicks.com/James. Use code James for a first deposit match up to $100. That's the easiest $100 you're ever going to make. So that's prizepicks.com/James and use code James. Daily fantasy sports made easy. The future of learning is definitely online. Like, it's such BS that you have to spend $200,000 or take $200,000 in loans and go to some fancy school when it's useless. It doesn't guarantee you a job. Most employers, including me, do not care about degrees or grades or anything like that. We want to care that you love what you're doing, that you know what you're doing, in some cases that you have experience or that you're willing to learn. But people in general love learning and are curious. Like, the key to success is curiosity. And I think masterclass.com is the perfect model for online learning. I'm really happy they're sponsoring this episode. If you're going to give a gift, give the gift of learning. Masterclass makes a meaningful gift this season for you and anyone on your list, because both of you can learn from the best to become your best, from leadership to effective communication to cooking. Let me tell you some of the classes I've taken. I've taken comedy from Steve Martin. I mean, can you believe I can take a class from Steve Martin on comedy, or Judd Apatow, my favorite comedy director? I could take an actual class from him on writing. Wolfgang Puck on cooking. Dan Brown on writing, or Judy Bloom, who's been on this podcast, on writing. By the way, Wolfgang Puck also has been on this podcast. It's such a pleasure. I try to take classes all the time from masterclass.com. And whether you're watching Masterclass on TV or listening in audio mode in the app or on their site, the quality speaks for itself. It's like these Masterclass instructors are your own personal mentors that are going to help you reach the next level. How much would it cost to take one-on-one classes on comedy from Steve Martin or on chess from Gary Kasparov? You just wouldn't be able to do it. But it would cost hundreds of thousands of dollars. With a Masterclass annual membership, it's $10 a month. Memberships start at $120 a year for unlimited access to one-on-one classes with all 180 plus Masterclass instructors. So it's not just $120 for one instructor. You get all 180 plus Masterclass instructors. Boost your confidence and find practical takeaways you can apply to your life and at work. And if you own a business or are a team leader, use Masterclass to empower and create future-ready employees and leaders. That's the real education in today's world. So this holiday season, you can give one annual membership and get one free at masterclass.com/JAS. JAS, of course, stands for the James Altucher Show. So right now you can get two memberships for the price of one at masterclass.com/JAS. Masterclass.com/JAS. Offer terms apply. Okay, so the steady state, we basically now know it's not a static state.
Yep.
But is there a paradox in the steady state?
Yeah. So the steady state, the adherence to it, again, there's always like two different sides. There's two different political parties. They're not Republicans and Democrats, but they were kind of like those that were sort of still in the eternal state, static universe. They wanted to preserve that for the same psychological, perhaps, predilections that your grandfather or somebody else, or Einstein, thought the universe was infinitely old. And that is because that seems like a more natural thing to consider than creation ex nihilo, creation from nothing. And so they maintain that that model could still be salvaged. What was on the other side? What was the Republican versus Democrat back then? The alternative was a new theory that came about after Edwin Hubble and after Albert Einstein's theory of gravity, and it came to be called the Big Bang. Except it wasn't called that out of respect. It was called that out of derision by a man named Fred Hoyle, who was an eminent cosmologist who operated in the 50s and 60s. And he claimed that people who believed in the Big Bang, which was originally called the primeval atom, and we'll talk about that if that's relevant later on, but he believed that people that adhered to the Big Bang narrative, which is a creation out of nothing, essentially, that those people were dominated, that they were inescapably influenced by a psychological compulsion, these cosmologists, to believe in Genesis 1:1. He actually said that.
Because he's basically saying you guys are all referring to an analogy to let there be light.
Yeah, I mean, where's the evidence for that? We see static things all the time, and he had a way to correct this flaw, to keep things static, to actually keep things moving in a universe that was that had some of the vestigial relics of the static universe. It came to be called the Quasi Steady State cosmology, QSSC, and this cosmology featured some intriguing bits to it. And the most intriguing part of it is it avoided the perhaps killer flaws of the Big Bang. So the Big Bang, I should mention, it was first proposed by a Belgian Catholic priest whose name was Georges Lemaitre in 1927. He proposed that the universe would have expanded at the beginning of time. So that time came into existence, the universe came into existence, and he didn't want to interpret it. You'd think that somebody who's a Catholic priest will say, I'm guided by this notion of the Genesis 1:1, just like Hoyle would later say. But he actually shied away from that. And when the Pope, his nominal boss, I suppose, tried to get him to say things like, this proves the Bible is right, blah, 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 he would refuse to do that. So he had a tremendous amount of integrity, that his model was basically supporting his psychology, his worldview, his theology. And yet he refused to rely on that and to use that. And it's so funny to me because I see so many people, when our experiment Bicep 2 announced that we had discovered what we claimed was the first direct evidence for inflation, that on the same day on two different websites, one would say, you're going to win a Nobel Prize, this team is going to win a Nobel Prize because it proves that there's no God. And then another website would say, this team is going to win a Nobel because it proves there's a God. So it's just so funny that both sides were so willing. And in the end, of course, spoiler alert, it's losing the Nobel Prize. So we were proven wrong.
Classic book.
Thank you very
by
much.
Dr. Brian Keating.
That's right. Ranked in the top 100 cosmology books of all time.
So
Yeah.
let me connect the dots a little bit to get to Lemaitre.
Yeah.
So in order to avoid the paradox that why aren't we seeing just all light all the time, all around, you would have to say something like, now that we know that the universe is not static, that all of these galaxies or stars are going away from us at faster than the speed of light. And that's why we're not seeing all or most of them.
Yeah.
And then you have to kind of just say, well, if they're going away from us, what happened a long time ago? If
Right.
you just rewind, where did they all start?
Exactly, right.
And unless they're just crisscrossing the galaxy somehow, just going back and forth, I don't know. This guy Lemaitre must have said, it has to come from some primeval point.
Yeah, and he called
Why
that.
can't they just be going back and forth though on the galaxy, like just some sort of roller coaster ride?
Well, if you go through them, I don't know if you ever played the game Asteroids, but
Yeah.
you travel through the asteroid belt. It's pretty dense out. No, it's actually not very dense. But if you take all the matter in the universe and put it all into one place, you've been to some crowded places, I'm sure. Imagine like every piece of matter, every black hole, every star, every planet, every podcaster, all crammed into an infinitesimal speck of size, potentially.
That would be a disaster if it's all the other podcasters. I
Now,
definitely don't want that.
Yeah, there's no social distancing back then. So the issue became that if you took it at face value, all the galaxies are moving away from each other now. As you said, rewind the movie backwards. You rewind it backwards. Everything is closer together yesterday, another yesterday, 13.8 billion yesterday, years times 365 yesterdays. If you extrapolate back, they were once in complete contact with each other. And what he claimed is that you would have an atom, that the universe started off as this enormous atom, not an infinitesimal atom, as later would be conjectured, what's called a singularity. And that brought up other sorts of problems that we'll get into. These were flaws with the Big Bang. These were ways for cosmologists to deride it and actually hoist it on its own petard. I don't even know if anyone knows what that means anymore. But basically take something that's a prediction of the theory and use it to ridicule the theory itself. So one of the things they did is they said, well, let's measure how fast the galaxies are moving apart from one another today. Let's extrapolate that back. How close were they yesterday? Keep going back and say, how old is the universe when they were touching? Now we know that's 13.8 billion years. Back then, they got a number of about 2 billion years. For a variety of reasons, Hubble made a misunderestimation, as President George Bush used to say, that the expansion rate was too high, implying that these galaxies weren't traveling very fast or they were traveling extremely fast, so they didn't have to be going for very long. Remember, distance equals rate times time. So he measured a rate that's about 7 times too high, which meant that the age which they were touching, the elapsed time, was 7 times lower than we know it is today. So say today it's about 14 billion years, divided by 7, you get 2 billion years. Now, even at that time, they knew of like radioactive elements. They knew the age of the Earth was at least that age, and maybe some of the stars in our galaxy were older than the age of the universe itself. It's like you being older than your parents. It was very strange. So people made fun of it. And every other year, they'd come up with some other value. It would oscillate. It would be changed by a factor of 10 in each direction. And so people had zero reason to take it seriously.
Although I get it, because everybody's trying to come up with a nice, neat, clean theory, and the Big Bang sort of gets there, and we'll discuss it more. But it could be the case that, let's just mix some theories. It could be the case that some of these stars or galaxies are not stars and are existing outside of what we call gravity, and others aren't. So those things collapse into something primeval, and other things might have been around longer than the universe, potentially.
Yeah.
I'm just making stuff up.
No, it's true. It's actually true that the ultimate theory that is in most sway nowadays is called inflation. It has features in it, including something kind of like this dark energy, this exponential expansion that kept the universe from collapsing in Einstein's model. Remember, his blunder was that he called it a blunder, not that it was actually a blunder. Instead, there were elements of the correct cosmological model, correct meaning what we believe to be true today, that existed not in the Big Bang model, but in the steady state model, in the quasi steady state. So nobody believed that the universe was actually static, but they did believe that there was creation of matter, that there's creation of energy, and that creation of matter and energy was producing the impetus, the rocket fuel, if you like, to get these galaxies to move. It turns out in cosmology, from Einstein's theory of relativity, that the more matter you have in the universe, the faster it's going to expand. It seems a little bit paradoxical, except when you realize, you can have something traveling. Let's say you throw up the ball. You're throwing it to one of your daughters. You throw the football right at her, and you throw it a little bit up in the air, and it comes back down. When it goes up, it's traveling with a positive velocity upwards by convention, and then it switches, and then it goes negative, right? It goes down. So at some point, it had to go through what's called an inflection point. It had to go from positive velocity going up to negative velocity, meaning going down. Remember, velocity is a vector. It has some amount, like 10 meters per second or miles per hour. I don't know how fast you throw a fastball, but it's quite fast. So it has some number, and then it has a direction. It's going up, it's going down. That's called a vector. A vector is a number plus a direction. So it's not maybe the speed itself doesn't change, but the direction goes from being up to down. So it had to go from positive to negative, and you can't go from positive to negative without going through zero, right? So at some point, its vertical velocity is zero. That's the apex. That's the highest point on a parabolic path that you'll get to, and then the thing will come down, right? Does this all make sense, or am I?
Yeah.
Okay. Now, what's it?
So I was just trying to figure out if the more mass you have, I'm trying to figure out why that would. Let me just think for 1 second. So essentially, if you have a lot of matter, you're probably just by E equals mc squared, the mass equals E over c squared. So at some point when you have a lot of matter, you're going to have more energy, which is going to create, I don't know what, but more speed or more velocity.
Yeah, in this case, it's related to that, but it's more related to the following fact, which is what is the acceleration of the ball? After it leaves your hand, what's its acceleration? Do you remember from physics how fast something accelerates in a gravitational field?
No.
So it's like 32 feet per second squared or 9.8 meters per second squared. And that means that every second, it will increase its speed by 32 feet per second. That's what acceleration means. It's a change.
But not forever, right? It stops at...
Well, but in the case of...
The acceleration is fixed.
The acceleration is
velocity
fixed,
not.
right. So the acceleration depends on the Earth, not on how fast you threw it. So they're totally independent. So the universe could be expanding, and it could have a faster expansion, and it wouldn't collapse because it has more mass, because that's totally separate, right? So what determines the expansion rate, not the expansion deceleration, is the amount of mass. And it turns out the acceleration or deceleration doesn't necessarily change its character unless you add in new types of matter, which have new other types of behaviors that we won't get into. But the reason I bring this up is because in the quasi steady state, remember, this is kind of like they have to add on like an epicycle. They have to tweak their model. They have to add a new feature to rectify the bug that was the observation that the universe is not static. How do they do that? They did it by invoking a type of force field that, instead of being like pushing on things, actually little bits of matter would pop out of the vacuum every so often. So the emptiness of space throughout the entire cosmos, matter would be spontaneously created.
Okay, but wouldn't you need energy to create matter? So where would the energy come from to create that matter?
Right. So part of the problem was, how do you create that energy field? We actually have that problem in quantum mechanics all the time. We have things that are called virtual particles that can pop into and out of existence. We have antimatter particles that have opposite properties, opposite charges, opposite other features of ordinary matter. But in quantum mechanics, you can what's called pair produce. So two photons can come together. And you ever heard of the principle of conservation of matter? No, you haven't, because it doesn't exist. There's nothing that says that matter is conserved. Energy is conserved. You cannot create or destroy energy. You can create or destroy matter at will if you happen to have a particle accelerator or something like that. And it turns out that if you have two beams of light on just the right properties, just the right energy, they can pop out of them two antiparticles. So a particle called a positron, which is an anti-electron, and an electron, or a proton and an antiproton. So light can actually interconvert and produce energy. Or you can say energy can produce matter, and that matter can then interconvert, destroy perhaps, and become light or energy. So matter can be created from energy. The question is, where does that energy come from? It comes from something called a scalar field. I'm not going to get into that. In quantum mechanics, suffice it to say, you can produce matter from what you consider nothing, but it has to be energy there. So by E equals mc squared, like you were saying, you can interconvert energy, but you have to presuppose that energy field exists. So they claim there's an energy field. They don't know what it is, but all it had to do to match observations was produce one hydrogen atom every century in a volume of space the size of the Empire State Building. So every century, that's all you need. One hydrogen atom, boop, pop out from some photons coming together perhaps, and you would have enough matter to drive an expanding universe that matched the observations at that time.
Okay, but here I have to ask, where do you filter the ideas? Because now it's just like, our entire view of the universe is wrong, so let's figure out some science fiction way to create matter out of nothing, like a magic trick.
Right.
And then we'll just all agree that it works, and that's our new theory.
It was so fun. In this case, what happened was one of the observations by Fred Hoyle, whose model this is connected with, he had two colleagues, one of whom I'm sitting in his former office here at UC San Diego. His name was Jeff Burbidge. Another one is Jayant Narlikar, who's going to be on my podcast, Into the Impossible. And then Fred Hoyle, who was this domineering figure of cosmology, happened to be on the contrarian side to what we now know to be correct. They came up with this model that would create all these different things, but it also turned out that Hoyle and Burbidge were making predictions about the properties of what are called the lightest elements on the periodic table. So the abundances of hydrogen and helium owe to the properties of the universe and its past. So what we see today either had to be created at the inside of stars. In their model, there were stars, but there was no beginning of time, right? There was no single Big Bang when you could synthesize these light elements, hydrogen and helium predominantly. So what they had to do is say that stars somehow made these new elements, in exactly the proportion that we see today. Namely, there's about 75% of the universe's elements are hydrogen, 24% is helium, and the rest 1% is everything else, the schmutz that we're made up of.
Right. So that begs the question. It's almost like looking at the same problem as if all the galaxies are flying away from us, eventually you have to rewind it and come into this primeval point. It's the same thing there. You can't make, I don't know if they knew that then or when they knew this, but in the center of a star, it's like nuclear fusion. So you're fusing these atoms together, a couple of heliums, you pull it apart, put it together, it's a carbon.
Right.
So you, at some point you have to unwind that. You can't just, they're not just creating the matter.
So they did. Exactly. So they had this cyclical behavior of the size of the universe where it would expand to some maximum rate, like the peak of the ball that you're throwing to your daughter, and then it would come back down and collapse, but it wouldn't collapse into the singularity, into an infinitesimally small, infinite density and infinite temperature. So on one hand, you had this kind of contrivance, like, okay, well, the universe creates all the matter that we see in terms of helium and hydrogen inside of stars. But the stars we know don't last forever, so they have to be continually created and destroyed, and they track with this field of creation of energy field called the C field in their model. Or you could say, all right, well, that's no good. Let me take the Big Bang model. Okay, well, the Big Bang model predicts that sometime in the past, the universe was at infinite temperature and infinite density. Let me ask you for a second, what's wrong with that? Have you ever seen something that's infinite?
I mean, I guess... No.
Einstein used to say there's only, two things that are infinite, human stupidity and the universe, and I'm not so sure about the universe. So he had all these pithy quotes.
But I guess you could say Zeno's paradox, when you look at anything, you're looking at an infinite bunch of halves.
But I'm saying physically, like they're talking about the universe, right? So they're talking about something that theoretically, if an observer existed, he or she could stick a thermometer into it and they would measure, here's infinity. And it's actually related to Zeno's paradox. Very perceptive you say that, because how does something go from being infinite to being finite? We know the temperature of the universe is finite today. It may be hotter in certain locations, like the surface of the sun or Boca or wherever you are. But the temperature how do you transition from infinite physical temperature to finite physical temp? Like at one point it's infinity, and then like my kid will say, I love you, infinity plus one. Well, then the next day it's infinity minus one. It's still infinity, right? So infinity, there's different types of infinity. Maybe someday we'll talk about the different classifications of infinities and how you can play games with different numbers and get these infinite sequences and so forth. That's a very interesting question, but that's just math. In this case, it's physics. So you have to explain, how does something of infinite density transition to something of finite density? That's an unsoluble paradox, right? So we don't have any example of that.
So the way you would do it in numbers is by taking a subset.
Divide by zero, right? Or dividing by zero or something, but you can't, you've never seen an infinite quantity of something, right? If there's an infinite amount of stars, like not just 100 trillion stars, as we might think there are, but there's an infinite number. Like again, you're gonna have like Olber's paradox again. So there's no example of something that's infinite in a physical world. In math, you're right. In math, you can have a series, but that's a conception of the human mind. And what's so interesting is that a computer is not as good at approximating infinities or infinitesimals as the human brain. And there are all sorts of cutoffs. And this will dovetail later, we probably won't have time, into the simulation hypothesis, because
we're going to have time for that one.
Okay, good. So here are your choices, James. You can vote for an infinite temperature, infinitesimally small thing, which we have no concept in the physical world, not in math. We can, our brains are pretty adaptable, but physically infinite quantity of something, a temperature, density, whatever. On the other hand, you've got this like kind of spurious thing that has to like, oscillate, create matter. And yeah, I kind of made it sound like, as they did, he was a very smart guy, Hoyle. He was very good at salesmanship, and it's underappreciated.
Yeah, but how does he get over the fusion problem?
So that was what actually ultimately did him in. He was so prescient. You just kind of glossed over it a little while ago. You said, you take a couple of helium atoms and you make a carbon. He was the one that discovered how that takes place. And he said that it must take place, this triple alpha process. We won't get into it, but you take 3 helium nuclei and you can make a carbon nuclei. So carbon 6, atomic number. You can take these objects and put them together, but the problem is they have to stick together. And when you bring positively charged things together, what happens? 2 positively charged protons. What happens to 2 protons when you try to get them together?
They separate.
They repel each other, right? They opposites attract and likes repel, which is good advice in marriage as well. So you have these 2 things. So how do you get 6
You
positive?
think that's good advice, actually?
Opposites attract? No, all the opposites that I had, don't no longer talk to me. But I'm happily married. So
that's a bad idea.
Yeah. But my wife is pretty different from me. Actually, I have to think about it.
But you probably have similar values to her.
We have very similar values, and I think that's the most important thing, obviously. But thinking about how to get these things together that are like charges required this very, very improbable state to occur called a resonance. And Hoyle predicted that would happen. And then another guy measured it to actually occur in his laboratory. And the guy who measured it won the Nobel Prize. His name is Willie Fowler. And the guy who predicted it and really came up with this idea, what was his basic idea, James? He said, we're made of carbon. Therefore, this thing that you think is impossible because there's like charges that repel each other, it has to be possible. It's called anthropic reasoning. You reason from our existence that certain conditions must be in place. And that still takes place in cosmology today, which we'll get to when we talk about the multiverse.
So basically, you're saying that the core of a star has so much energy and has so much mass. Protons are trying to get away from each other, but they can't. They're just crushed into each other.
They get bound for a millionth of a second, something like that. It's very, very tiny fraction. They go into what's called a resonant state. That resonant state is just enough time, energy, pressure to fuse. And if it didn't occur, if the carbon energy structure was slightly different, we wouldn't be here asking about how did carbon come to exist? Because we think all life has to be carbon-based. So here's a guy who made predictions like that, titanic intellect. He was actually a really extremely harsh critic, much worse than I am, of the Nobel Prize, which a lot of people believe is why he didn't get it, completely undeserved, because he actually was an amazing scientist. He would look even for flaws in his science. So he was the kind of guy that you would want to be around all the time, because he would make these pejoratives. I didn't say what the Big Bang stands for. I didn't say it last time because I knew my kids would listen to that episode. They're not going to listen to this episode. Big Bang in British English means orgasm. So he coined that term in utter derision to like what he said. Was the universe orgasming? What is God having this orgasm? And again, he was a vehement atheist, completely, militant, unrepenting atheist. But he was so brilliant that he would follow the data, even if it meant that it was going to be used to falsify his claim that these stars could be somehow continuously sourcing the amount of hydrogen and helium. And I won't get into the details. I describe it very briefly in my book, but I care more about his psychology. Imagine that. You have this like theory. The whole world's on one side. You think they're totally mashugana, as we say, but you realize that you're right and you can prove it. And then, oh no, there's a math error. There's something wrong.
Okay, let me ask though, because let me just play the devil's advocate on behalf of Fred Hoyle.
Yeah.
So everything's expanding. And gradually, as things expand, they move further and further apart. And maybe there's some process where stars turn into smaller stars, turn into their components, turn into carbon, and then eventually even that starts expanding apart. So the carbon has some sort of fission, turns into helium, hydrogen, whatever. So now we're at this point where most of the universe is in the middle rather than at the fringes. So it starts comes back into suns and stars, the carbon starts being made, but then all the energy of the sun's being used, conservation of energy, so there's no more carbon could be made. Now when the protons start to get close to each other, they're powerful enough to expand out again, and that starts the re-expansion. Well, so I'm playing devil's advocate for him.
Yeah, so you could actually work through some of those scenarios, and people did try to do that. ultimately, what you'll find is you have to solve several different mysteries at once. You have to overcome forces on multiple scales. So gravity is the weakest force, but it acts over the longest ranges in the universe. The nuclear force that bonds these two protons together when they should be repelling each other is much stronger than the electromagnetic repulsion of the two charges, which is still 40 orders of magnitude stronger than the gravitational force of two proton masses separated by some distance from one another. And so if you work through all the different physical forces that can be present in the core of a star, or perhaps in an evolving universe that's slowly creating matter, that was the least of their worries. Their bigger worry against Hoyle was, this field that's continually creating matter, it doesn't explain how you're going to produce the elements that we know to be the most abundant elements. And it's not even close. So they ended up not exactly recanting that. They ended up saying they kept adding on different epicycles to their theory. But what's so interesting, and they would modify it every couple of years, they'd come out with a new and improved quasi steady state. Anytime you have to add a modifier, right? So there's an adjective, quasi, meant it's not really steady state. So then why not just reevaluate the entirety of this paradigm? And that's ultimately what happened. But it wasn't until a measurement done by the pioneers of my field named Penzias and Wilson that the era of actual experimental cosmology took place, where we could build an experiment that could measure a property of the universe. And from the data, we could divine the properties of the early epochs in the universe. And that was in 1965. And that was a huge hurdle for the quasi-steady state cosmologists to overcome. And I see this nowadays. There's only a few people that are working on alternatives to what's called the theory of everything. So we had a couple of webinars with PBS Space-Time Studios, a huge channel on YouTube run by a friend of mine, Matt O'Dowd, who's an astronomer, PhD. And we had a series of 2 webinars with the leading lights of physics. And the question is, do we need a theory of everything? Does a theory of everything get mandated? And what does it mean to be a theory of everything? Remember I said those forces of nature, gravity, electricity, and the nuclear forces? There's 2 nuclear. The question is, are they all manifestations, different vantage points of a single theory? In other words, we perceive gravity to be different from electricity and magnetism. You get a shock from static electricity. But what if at extremely early times in the universe's history, they were actually just one force? And that one force transitioned into different manifestations that we see nowadays. We actually have very good evidence that the nuclear force and that or perhaps the nuclear force is called the weak force, and electricity and magnetism are all one thing, called one force, so it's called electroweak force. So there's evidence for this. The question that we're trying to answer with Eric Weinstein, Lisa Randall, Sabine Hossenfelder, Lee Smolin, James Beecham, and Stefan Alexander was, do we really need this theory of everything? Or, is that just a prejudice that human brains want to always unify things together? Because it's simpler to think of one thing, right? It's easier to say, there's just one force, instead of there's 4 different forces, gravity looks like this, electricity looks like, but the question is, did it occur to them in the early universe? Did that property take place? And I see with people like Eric Weinstein, our mutual friend, that, he's really far out of the mainstream, so to speak. He's got his own ideas of how a theory of everything should look, and it's very different from the dominant paradigm called string theory. That doesn't mean he's wrong, but a lot of people say, well, history doesn't really play out well for the Mavericks, right? So the people that really, like Hoyle, who thought differently than the accepted wisdom of their age, never really accepted that he was wrong. And the question is, do we see the exact same thing happening because of not physics, but psychology and almost like peer pressure?
Small business owners are savvy and know how to get maximum value from their monthly business purchases. The enhanced American Express Business Gold Card is designed to take your business further. It is packed with benefits and features like 4 times membership rewards points that automatically adapt to your top 2 eligible spending categories every month on up to $150,000 in purchases per year. So you earn more where your businesses spend the most. Plus up to $395 in annual statement credits on eligible business purchases at select shipping, food delivery, and retail subscription merchants. So with flexible spending capacity that adapts to your business and access to 24/7 support from a business card specialist, you can continue to run your business with confidence. The Amex Business Gold Card, now smarter and more flexible. It's got the powerful backing of American Express. Enrollment required, terms apply. Learn more at americanexpress.com/business gold card. This is such a valuable service for all business owners, big businesses, small businesses, doesn't matter. I wish I had this in the many different businesses that I've started. Sometimes it seems like your business is humming, but then suddenly you don't understand it. You're starting to fall behind. You're not understanding where your costs are, where your revenues are, where your payments are. Teams are buried in all sorts of like BS work, and you can't seem to close the books. So you need like one dashboard, one source of truth. I'm jealous of this business, NetSuite from Oracle, of course, NetSuite by Oracle. I wish I'd come up with this idea. It's a brilliant concept to have all your business intelligence on one dashboard. This is why you need to know these three numbers: 37,000, 25, and 1. So 37,000, that's the number of businesses which have upgraded to NetSuite by Oracle. NetSuite is the number one cloud financial system, streamlining accounting, financial management, inventory, HR, and more. 25. NetSuite turns 25 this year. That's 25 years of helping businesses do more with less, close their books in days, not weeks, and drive down costs. 1, because your business is one of a kind. So you get a customized solution for all of your key performance indicators, your KPIs, in one efficient system with one source of truth. Manage risk, get reliable forecasts, and improve margins. Everything you need to grow all in one place. So right now, download NetSuite's popular KPI checklist designed to give you consistently excellent performance absolutely free at netsuite.com/James. That's netsuite.com/James to get your own KPI checklist. netsuite.com/James.
At FedEx Office, we know that for small businesses, the holidays can be stressful. But we're here with the holiday cheer and expertise you need to help get your to-do list done. Need to create that? Our online design tool has got you covered. Pack and ship these? Just come in store and we'll take it from there. Print those? How does same-day turnaround sound? This season, let us help you slay the holidays with the products, services, tools, and timelines that will make your business bright. Create more happy for the holidays at office.fedex.com.
Right now, we don't have a theory of everything, right?
Yeah.
You say there's these theories of this one force, but there's also the fact that, quantum mechanics, breaks some of the laws of relativity that, basically when you're examining tiny things like, quantum particles versus galaxies, the rules break down, or they're different. They're different rules, we think. And there's no unifying theory.
Right.
So your point is, why do we need a unifying theory? And do we need one?
Yeah.
Is it a psychological thing, or must there be one, or else the universe can't exist?
And it's relevant and pertinent to what you and I are talking about, because as we now know, the properties of the universe on its tiniest, microscopic, infinitesimally small scales determine its macroscopic properties. So the sun is enormous, 1 million kilometers across, something like that, just enormous in size. Why is it that size? Partially because of the way that nuclear reactions take place at the nano scale, at the quantum scale, the scale of a single proton. Those are determining the properties of this enormous thing that's millions of kilometers across. And so we now know that the physics of the ultra small determines the appearance of the entire universe. So these are very pertinent questions to when we discuss some of the cosmological models that we'll get to, because different approaches seek to incorporate various physicists' approaches to the unification of the 4 laws of physics. And it's usually just gravity that doesn't play nice. Gravity is somehow mysterious. It's very different.
And by the way, just to mention, your whole idea of the telescope, Bicep 2, that you've built, is that instead of looking for light to find, usually we look at a galaxy, the light of a galaxy and how it's changing, and that's how we could determine properties of that galaxy and how far away it is and how it was constructed. But you're saying because the cosmic background radiation acts like light and gravity isn't, let's build a telescope that measures gravity so we can see past it for the first time ever.
Right. We can use another type of signature, a messenger, in this case, gravity, which goes through everything. So gravity goes through everything, which you can tell because you and I can both have high tides in San Diego and in Florida at the exact same time because the gravitational force of the moon goes through the mass of the Earth. So gravity is very weak, but that's a good thing because it allows us to trace the properties of things that are very far away without getting absorbed. There's no way to absorb gravity. So these waves that you talked about where, when we were talking about Olber's paradox, you're actually right. There could be dust that absorbs it. There could be whatever, and eventually it would heat up. But if the universe isn't infinitely old, it doesn't matter. But that was one of the things we were trying to disprove. But gravity, there is no dust. There's nothing that can get in the way of gravity. You can't stop it. You can't control it. You can't guide it. Unlike every other form of radiation, can be contained, guided. That's how we use radio waves, fiber optics, control light. You cannot guide gravity. And the other way that's very different is that there's only one gravitational charge, right? There's not like a positive gravity charge and a negative gravity charge the way there is with electromagnetism. But that's very weird because we know that they both obey the inverse square law. In other words, if you have a positive charge and a negative charge, and you move the negative charge twice as far away from the positive charge, it will feel an electric force that's 4 times lower than it did when it was half the distance. That's the inverse square law. The same thing happens with gravity. If you have the mass of the Earth and the moon, and you move the moon twice as far away, the gravitational tides, the force on the Earth, etc. Well, the tides will change more steeply than this inverse square, but the actual force on objects will decrease as the inverse square.
So then, because these things that on the surface seem to have nothing to do with each other, these two completely different types of forces, the fact that there's this weird constant of how they change over distance or time, sort of, is that where the one force aspect comes in?
Yeah. So you start to think about, well, in what ways are they similar? Another manifestation is light. So if you have a candle and you're moved twice as far away as you are now, the candle will appear 4 times dimmer. If you have a source of gravitational, force and you move twice as far away, you'll feel 4 times lower force. And actually, the equations for light, the propagation of the speed of light, are almost identical. Those are called Maxwell's equations. They're almost identical to the Einstein equations, which govern how gravitational waves propagate. And if you solve them, they both have the same propagation speed, namely the speed of light. But in some other universe, we might call it the speed of gravity. There's no reason to say that it's fundamentally a property of light rather than a property of gravity. And maybe that's a hint that the ultimate, unification has to encompass this kind of Janus-face duality between how we perceive a gravitational force versus how we perceive an electric or magnetic force. And we just don't know. But that's one of the projects in physics. And actually in the zeitgeist, in the spirit of the times right now, there are all sorts of I think it's like end times, because there are all these new theories that are coming out about how the theory of physics could be unified into a theory of everything, to have a t-shirt sized equation, you could write down how light behaves, how gravity behaves, quantum mechanics, all those things in a single equation. And again, getting back to our conversation, they have to then be examined for their predictions about how the universe is evolving and composed.
So, going to the Big Bang, because this is going to be related, the Big Bang happens, this infinitesimally small point, something happens, it all explodes. Within a couple trillionths of a second, it expands out, a huge amount. Particles are booming out faster than the speed of light. And then 380,000 years later, they're starting to be big enough, I guess, that they start combining, forming hydrogen, helium, other atoms, and that's what initially created, they're not really solid yet, but that initially created this cosmic background radiation. So let me ask this. What if, when you're trying to figure out what that infinitesimally small thing is, maybe we always think in terms of particles or something that exists. What if it was just waves first, and the first inflation was really the waves turning into some other waves, and then those waves turning into some kind of particles, and so on?
You're actually bringing up something that happens all the time in physics. Here's a good example. There's basically this duality in physics that sometimes you have to change the properties of matter in order to match observations and conjecture unseen new types of matter. And sometimes you have to change the laws of physics itself. So in other words, the equation side of things has to be changed. I'll give you two examples. One is when people were looking at the orbit of Uranus. No jokes. Come on, you can't say that and not get a laugh. You can't do that.
You got to go on stage with that one.
Got to go around that. So, but if you do look at that, when you look at the properties of Uranus, it had certain anomalous behaviors that could not be explained until astronomers conjectured that there was a planet even beyond Uranus that you couldn't see with the telescopes of the time, but they actually could predict where this planet would be that was totally unseeable, for a very long time. And they predicted it, and that became the planet Neptune, and it was found exactly where these astronomers predicted it would be found.
Right. So with any two objects,
yeah.
If you all you think is that there's two objects there, then using the laws of gravity, you can predict how they move, and if they move even slightly differently, there's something else that has a pull on it that you can't factor for.
That's a possibility. Except now we're going to go in a different direction. So when this planet was discovered, and various people worked together to independently discover this in the 1840s. This discovery was basically a discovery of dark matter, of previously unseen matter. And now this huge giant planet that's got this huge diameter at great distance, the farthest planet away from the sun, now that Pluto is no longer a planet, right? This discovery relied on the conjecture of a chunk of matter. It wasn't like exotic matter. It was just a ball, like a planet, like the other 7 planets. In this case, that was predicting that there was matter that we hadn't seen, but if we looked in the right place, we would see it. Now, on the other hand, Mercury, the closest planet to the sun, was known for many hundreds of years to display an orbital property that was not possible to be explained without the addition of another planet like closer to the sun, which became called like planet Vulcan. Or what Einstein did is he said, no, when you get too close to a very, very massive, heavy object like the sun, the laws of gravity aren't the laws of Isaac Newton anymore. So in other words, these scientists in the 1840s used just Isaac Newton's laws, and they successfully predicted where there should be an unseen companion to the planet Uranus. But Einstein said, no, actually, Newton is wrong. When you're close to high gravitational force fields, he's fine when you get far away from them, like very far away from the sun, but he's incorrect. So he had to change the laws of physics. So in that case, adding dark matter was wrong. Adding unseen matter, Vulcan, was wrong. Instead, you had to tweak the laws of physics to make it compatible with what you saw. And so it's very unusual because actually now we have that problem today. There's something called dark matter. There's another thing called dark energy. We don't know almost nothing about dark energy, but dark matter, there's some different conjectures. Some people say it's an exotic form of particle matter that's just very different. Like there's like a dark periodic table. There's just matter that doesn't interact with light, and there's matter that doesn't interact with matter that we're made up of, protons and neutrons and croutons. But in the case of the other side,
you prepared that one.
That one's
used that one
that's
before.
cosmic gold, James. But in the case of their opponents to that, they say no. Actually, on very large scales, now you're going beyond the size of the galaxy. Now you have to modify Einstein's equation. So Einstein was wrong when you consider the ultimate largest scales in the universe, and now they have to change the laws of Einstein. So it goes like this: it goes the modified Einstein equations. Then when you get really far away from the Earth, or at great distances in the cosmos, down to the size of the solar system and gravitational fields of our internal galaxy, and then it changes when you get far out to like become more like Newton on the scale of actual proton of our solar system. So that's called modifying gravity now. So it's kind of following in that tradition. The other people are kind of following in the tradition of the 1800s, looking for unseen matter and possibly new forms of matter itself, matter and energy.
So could it be possible dark matter and dark energy don't exist? It's just one attempt at solving these unsolvable gravitational problems? Or the other thing is it just could be there's different rules that we don't understand?
Exactly.
Because we've never detected dark matter. We're just theorizing it.
There is one form of dark matter that I seem to be one of the few people that makes this point, but I'm sure other people have made it. There's something called neutrinos. Neutrinos go through a light year of lead before they get stopped or absorbed. They go right through you right now. There's trillions of them going through, produced by nuclear reactions in the sun. On the other hand, there's also reactions that are occurring that produce them that they will slowly and very rarely interact with matter on very, very improbable circumstances, but that will occur. And you can actually get them to create new forms of matter, things like called neutron stars and so forth. But that is a form of dark matter. It doesn't give off light. It doesn't interact with matter except extremely rarely. So it has these different properties that dark matter has, and it has mass. So these things are the lightest, most massless, almost massless, but they have a tiny bit of mass. So the lightest ordinary particle is called the electron. These are fundamental particles, meaning you can't split them into other things. We think that they're elementary particles. The proton is not. You can split the proton into 3 different quarks, it's called. We believe the quarks are fundamental, but we're not 100% sure. They may be composed of strings, and we're not sure about that. But neutrinos, you can't subdivide into anything. They're elementary particles. They are the weakest interacting particles, and they have a mass that's lower than 1/1,000,000th of the mass of the lightest ordinary particle called the electron. So these are very bizarre things. They're kind of like dark matter, and they behave as if they are, but they can't comprise enough of the dark matter to explain the properties of the universe we see today.
So wait, with my theory that all the waves kind of condensed into this infinitesimally small point and then inflated out and started, the waves combined in some version of their chemical reactions to create the weak forces, the strong forces, gravity, light, and then those kind of combine in various ways to create hydrogen, helium, and so on and so on. Maybe the flip side was the dark matter and dark energy are all the waves that didn't fall into the family of waves that created light, gravity, blah, blah, and so on.
Exactly.
And maybe there's a tiny mass of each. Do waves at all have a mass? Because now sometimes they're called photons rather than light waves.
Yeah.
Sometimes they're called gravitons rather than gravity waves.
Right, exactly. So it's kind of like depending on what energy scale you're participating at, a photon will behave like it's a particle, or it could behave like a radio wave is a wave of light that has the properties. It has a wavelength, it has a frequency, it travels at some speed. On the other hand, photons don't have any mass, so they're massless. Gravitational waves or gravitons are the gravitational analog of very, very short wavelength, which means very, very high energy particles of gravity. So we actually have never detected those particles. We've detected waves of gravity classically, which are kind of like detecting radio waves. So the way that things get detected, usually you first detect them in their so-called classical state. Namely, we detected, a spark of electricity. Heinrich Hertz made a spark, like a spark plug in his lab, and then a spark plug across the room illuminated. Like another spark went off when there was enough energy zapping out of one, and it traveled at the speed of light to the other one. Those were waves going through the atmosphere of the laboratory, and they have a certain characteristic wavelength, and they interfere with each other. You can make different patterns. You can have cancellation. But when photons, like you have a high energy gamma ray or something like that, you really don't think about it as a wave that has this kind of infinite extent in terms of space.
But if they have no mass at all, can they somehow convert some of their energy later into mass? Can a photon ever?
Yeah. So actually, So it's almost impossible to get a radio wave. So again, to create new matter, you need at least 2 photons, or you need 2 things that have the same charge that come out in the end. So let me say like this: photons have no charge. So if you take 2 photons moving in opposite directions, as long as they have, each one of them has the energy of an electron's mass converted into energy. So you take the electron's mass equals mc squared. You have a machine, a gamma ray generation machine. It's about 0.5 kilo electron volts. That's the technical description for how much energy that has. And you shoot one of those at another one traveling in the opposite direction, because otherwise they'll never meet each other. And they will have some probability to combine to produce not one electron, but to produce one electron and one positron, which is an anti-electron, meaning that it has positive charge. The electron has negative charge. Adding a positive to a negative, you get 0, which was the original charge that you put in. So energy is conserved because the mass that comes out is twice the energy of each photon divided by the speed of light squared. And the charge is conserved. We believe that charge is conserved, energy is conserved, something called momentum is conserved. We're not going to get into that, but mass is not conserved, right? We went from 2 massless objects to 2 massive objects. So you can actually put enough positrons on a scale and it will weigh something. it'll actually have a weight.
Okay, so even though I'm just riffing on this, poke holes in my theory that I always think of the Big Bang as like all the matter that currently is in the universe was condensed into this infinitely or almost infinitely dense point, and then it exploded. Just riffing about how all these forces and waves might be the same. Couldn't everything have been ultimately broken down into this one type of wave that then combined to create more waves and forces, which then combined to create electrons and positrons, which then combined to make hydrogen and helium, and so on and so on. So couldn't everything start out as this one type of wave?
No, at certain points in that chain that you glossed over very expertly, you have to consider things as a particle. And ultimately, you think about we normally think about things as they're not actually particles, but if you zoomed in with some kind of super microscope, you'd see what's called a wave packet. You'd see like extremely high oscillations of the probability to find a photon at a certain point, and the amount of oscillation and the compactness of that bundle of waves is dependent on the energy of that particular photon. But on a small enough scale, when it gets to be about the size of the electron or subatomic particles, then you cannot really treat it as a wave anymore. It doesn't make sense to treat it like a wave. And there's no way to get a radio wave, which might have a wavelength of kilometers, right? So radio waves on the AM dial have wavelengths that are kilometers long, potentially. There's no way to combine those two and have electrons pop out of those. You need extremely high energies, which means extremely short wavelengths, at which point you should approximate them as actual particles, even though they theoretically could be made to interfere. So what does it mean to be a wave, first of all? It means that it has properties that are representative of waves, meaning waves interfere at the beach. You see swells and you see troughs and you see how they combine together. They make these diffraction patterns. You can't really get electrons to do that unless you have extremely high energies or extremely small distances, the double slit experiment, things like that. But those are all at very high energies. So your claim, your model, the Altucher model, requires extremely high temperatures and densities, but you're also requiring that they maintain their wave-like characteristic, which is impossible. Those two things are in opposition to one another.
So at some point, even if my model works, at some point before that, there still had to be mass and matter.
Right. So you had to treat them as a particle. Yeah, you have to treat them as a particle, right.
So could there have been one particle that then it was all condensed that first created the waves?
Yeah, so actually we know of enormous physical macroscopic nuclei. So they're called neutron stars. And they're, 10 to the 56th number of neutrons. And that's basically an atom composed primarily of neutrons, or almost maybe entirely of neutrons. And we have a prejudice to think of matter as like protons, but neutrons have mass and they exist and they have mass, they matter. And so the question of whether or not you can have macroscopically such large atoms, if you will, or nuclei is not an academic one. It's actually, we know that to exist. So if you look them up in the periodic table, it's way out 10 to the 56, not the 56 spot, but a 1 with 56 zeros after it. So such a periodic table doesn't exist. But nevertheless, we have evidence for it from detections by multiple experiments. And the question of whether or not you can actually conceive of all the matter being in an infinitesimal point, again, that's the problem that was pointed out by people like Hoyle. And even Einstein rejected Lemaitre's original conjecture that there was this primeval atom. And it wasn't until later that it came back into vogue. So on my list, we've covered the static universe. So we've covered the
static,
eternal,
steady, quasi-steady,
and hot Big Bang. So there's another type of Big Bang where the Big Bang is cold.
Like prior to the Big Bang Theory, everything that we're talking about has pretty much been seen or theorized in its components. Like there's atoms,
Yes.
There's light, there's gravity, there's these forces, but now you're talking about something infinitely small. What is that? And that's what we're just trying to figure out with, I was trying to naively figure that out with maybe it was this weird primordial wave that doesn't exist anymore because it's combined into all these other things except, but there's still, what's the theory of what's there and how did if there was no time or space before then, what does that mean? How did it then explode?
Right.
And then, of course...
Yeah, because how does time progress when time comes into existence. So
Yeah, and then there's also the question, which is related to your experiments with Bicep too. You think that 380,000 light years away from the cosmic background radiation, you're going to find evidence of the Big Bang if you're looking at the gravitational waves of the explosion. How do we know it was 380,000? How do we know that, since we can't see past that cosmic background radiation because it's filled with just this wall of atoms or whatever? How do you know it's not 20 trillion light years
there's something
away?
that happens very frequently, and I'm actually writing an article for Astronomy magazine. I know you're a lifetime subscriber. You read it for the,
I should.
You read it for the articles.
I'm going to be a physicist
No,
after
you
this.
would. You'd really enjoy it. It's a lot of illustrations, and then I'm also writing an article about one of these misconceptions, which is that the Big Bang and the origin of the universe are really the same thing. And they're really not. It's not just an academic or kind of semantic issue. When we say the Big Bang, most people that are lay people think going forward in time, like there was an origin and then it was really hot. And if you go earlier than a couple of seconds, it was super, super duper hot. But actually the way that you should think about it is not starting from zero, but starting from today and going backwards. And if you do that, you go back, billions of years in time, eventually you get to a point that's 13.798 billion years ago. And at that time, there was a plasma throughout the entire universe comprised of electrons and protons. That was basically all there was. There was dark matter, there was dark energy, but all that we care about was the existence of protons and electrons. And when you have protons and electrons, I can go into my lab down the hallway here. I can take a gas of hydrogen, which is an atom, which has one proton, one electron. That's all it is. I can heat it up super hot to a certain temperature of, tens of thousands of degrees. And eventually the protons and electrons will rip apart and you get a plasma.
Is the plasma just like the quarks swimming around in some soup?
It's not the quarks. You have to get much hotter to actually make the quarks ionize. This is just ionization of hydrogen gas. You can actually do it, with low amounts of electricity. You can do it with water. That's how certain hydrogen fuel cells work. It's not that you need tons. It's just one way to do it is to heat up the gas in a certain way. But you could also shock it with electricity with a certain amount of voltage per atom, and that would be sufficient to break apart. It would give you enough energy that the heat energy would rip apart the proton, shatter the atom into a proton and an electron. It wouldn't rip apart the proton into quarks, but that's not what's necessary. A plasma is just a gas composed of electrons or a gas composed of protons. And you can have two of them mixed together, protons and electrons. And you can even have nuclei. You could have, iron has 56 protons. You could have a gas of 56 electrons per iron nucleus. And then you could have a gas of, something that has 56 protons in the nucleus, but that's very rare. We normally think of plasma as basically hydrogen. And so it's a gas of electrons. It's like you could fill a balloon with electrons if you could do such a thing. That would actually be what's called a plasma. Now, if you take a plasma, and there's a plasma between me and you, at a certain time in the universe, this was true, light cannot get through a plasma. One way to think about a plasma is your mirror. You cannot see through your mirror because all the electrons in the aluminum or the silver or whatever are free to move about, almost like they're a two-dimensional plasma. They're confined to the surface of the mirror, and they do not allow light to go through it. So mirrors are opaque because electrons are really good reflectors, very good at reflecting light back away from the direction that it came in.
And the electrons won't repel each other?
So they do, but there's certain ways that they can conduct themselves in a two-dimensional surface or in a plasma. They organize themselves to produce basically like a repulsive pressure that keeps them enough apart from one another. But there's so many, you're talking about a trillion of them, that there's so many, there's a sufficient number of them to reflect any photons or scatter the photons around, jumbling them up so that no photon gets from your eyes to my eyes without getting scattered so much that I can't even see you anymore. Does that make sense?
Yeah, and so basically this cosmic background radiation is this plasma.
It's the heat that kept that plasma from forming into hydrogen atoms.
And then again, we theorize, or we know, I don't know, that 380,000 years before that plasma was formed, the Big Bang happened.
Well, the Big Bang, again, so don't call the Big Bang like time equals zero. Think of the Big Bang as doing two things: creating the lightest elements on the periodic table, creating hydrogen, helium, a little bit of lithium, which some of us care about more than others, beryllium, but basically almost nothing. So it's creating not almost nothing. It's creating all the important atoms in the beginning, but lithium, hydrogen, and helium. And they're isotopes. Remember, they're isotopes of these things that have different numbers of neutrons. These are the primordial fossil relics of the formation of the first elements on the periodic table. They still live. They exist to this day. You're made of the hydrogen in the water molecules inside of the liquid that's inside your eyeball, okay? Just think, that was most likely formed during this epoch of the Big Bangs, of the history of our universe. It wasn't created in a star. We know that, right? Because stars take hydrogen and they make helium. So you're not made of helium, you have hydrogen in water. That hydrogen was formed during this period of 380,000 years plus 3 minutes. It takes about 3 minutes at extremely high temperatures. What I'm going to get to is beyond that, we don't know what happened.
So how do you know it's 380,000 years?
Because if you take, and I think I gave you this example, if you watch these CSI Miamis or whatever, they come upon a dead body, they stick a thermometer in it. They measure the temperature of the room. The room is 80 degrees. The human body is 98.6 degrees. They can measure how long you've been cooling off for by the temperature that you are now. And they can set a limit on it as long as it's higher than the room temperature that you're at, then between, greater than 80 degrees or 65 degrees here in San Diego, they will be able to determine how long it's been since your body stopped producing the 98-degree temperature.
They know what temperature then the Big Bang happened at?
Well, what that's predicated, that CSI example, is that the human body is mostly water, and we know what's called the heat capacity, the ability of our muscles and our bones and the water to retain heat. And so it's material dependent. What was the material that the universe was comprised of a few minutes after the starting of the formation of these light elements? It was comprised mostly of hydrogen. So we know at what temperature hydrogen goes from being a plasma of electrons and protons to becoming a bound hydrogen atom of an electron orbiting a proton. That's what it means to form. That's called recombination. When an electron cools down, there's no longer enough bombardment from photons, and they can join, and now the electron can orbit around, and it makes a molecule, or an atom rather, of hydrogen. That happens with a characteristic energy that we know to like tens of decimal places. That's the analog of the human body temperature being 98.6. We know the initial conditions that the hydrogen was at in order to form, and we know before that it must have been higher than the 98.6 or higher than this 13.6 electron volts. And that means that it was in an ionized state beforehand, and then it kind of liquefies. It's like going from steam to water. We know what temperature that happens at. So that tells us the initial conditions, and then we measure it today, and that's like sticking the thermometer in the body now. We know how long it's been cooling off for.
So we know in the cosmic background radiation, at what point the hydrogen atoms started forming.
That was 380,000 years. It went from electron and proton to hydrogen atom at 380,000 years.
So we're able to say, well, okay, it takes 380,000 years to do that. Do we know that that's when the Big Bang occurred?
No, so the Big Bang had to occur 380,000 years earlier than that. But again, the last second, the last trillionth of a second, that's where going backwards in time, the first trillionth of a second, the first trillionth of a second, that's where all of our ignorance lies. In other words, beyond 1 second, let's say the universe did have a singular origin. Or let's say the universe collapsed, which will be one of our other models probably for next time, where the universe cycles through expansions and collapses. That's a perfectly tenable model even now. That means that there was a specific time when it reached maximum contraction, and there's different versions of that model that we'll talk about. But then a second after that, when it got to its minimum size, or if you like, if the universe did emerge from inflation or from a primordial, from nothing, ex nihilo, a second after that, that's when these nuclear processes start happening. And that's when the first protons and electrons are formed. But again, going earlier in time, it sounds like not a big deal. Like, oh, you can go all the way to 380,000 years. What's the last second? That's where all the interest is, right? Because we express time as logarithmically. In other words, the difference between a temperature of 100 degrees and 0 degrees is not 100 degrees. We think about it as orders and orders of magnitude, 2 orders of magnitude. We want to go to a decimal place followed by 36 zeros. That's the time scale at which inflation, if it did take place, would produce these waves of gravity.
So I know we have to conclude part one, but let's say your gravity telescope, the BICEP, was able to detect gravitational waves from 380,000 years earlier. How do you know that gravity even exists then? That could be a problem, that maybe in that trillionth of you're trying to find out the details. You're trying to find the geography of that trillionth of a second.
Right.
But maybe gravity is not a part of that geography at that point.
Yeah, so a couple things we have to believe are true, and then we just test how true or not they might be. So one of them is that, say, things like the speed of light do not change over time. In other words, they're actual constants of nature. The constants that go into the mass of hydrogen doesn't change over cosmic time. If those things did happen, it would compromise our ability to make predictions. But we assume that they don't. And then the question is, well, how do you know that the speed of light hasn't changed, or say the nuclear force hasn't changed in a billion years? Well, fortuitously, it turns out in the middle of, I think, the Congo in Africa, there was a naturally sustained uranium fission reactor, a nuclear reactor that was undergoing fission that was cooled by the inflow and outflow of spring-fed water into like an underground cave. It's called the Okolo Natural Nuclear Reactor.
I never heard of this.
It occurred a billion years ago when this took place, and they've measured it, and they've done and looked at the different the chemistry of it and the nuclear radiation that was present there, and they realized that this was a naturally occurring slow neutron moderated nuclear reactor, and the only way that could take place to produce the amount of nuclear blast or radiation rather that's suffused the cave and the marks that they have on it is if the half-life of uranium hasn't changed in a billion years. If the strong nuclear force constant, like the speed of light for nuclear force, if that hasn't changed in a billion years. They can say, well, maybe it's changed. It didn't change the last billion years, but maybe it changed between years 3 billion to 2 billion, and it just gets very contrived. So certain things, there are cosmologists that do work on this, that the speed of light has actually changed over the lifetime of the universe, and that can explain certain things more simply, the same way that conjecturing Neptune explains certain things more cleanly, but the modifications of gravity explain the orbit of Mercury better. So all these things have certain amounts of evidence and credulity that you assign to them based upon ultimately what you can test here on Earth. So in other words, if the properties of hydrogen have really changed, if the temperature at which it was ionized at is actually changing, and so then all bets are off, but we don't have any evidence for that on human timescales, billion-year lifetime timescales, et cetera. So then it's on you as a skeptic to conjecture some model that can change the properties of nature just long enough to affect the results of BICEP 2 in a way to make them imprecise and useless to predict what happened in the early universe. And that's a big burden for you to have on your shoulders, young man.
Sure, but at the same time, we know that first trillionth of a second, time is also being created. So there's lots of things
we don't know that. Actually, in some of the models we're going to get to, time doesn't exist at the beginning, what you'd call the beginning. So in other words, time comes into existence, but it comes from a space. So you take gravity and you take the structure of space-time itself, and it is encrypted with the ability that when you change it from being three-dimensional or two-dimensional, you actually can get what's called imaginary time. And this will be a great segue into next time. This is actually one of Stephen Hawking's last great, kind of conjectures, theories, which we really don't, and it was one of his first as well. It's called like the no boundary proposal. It basically solves certain problems in exactly the type of thing you're talking about. How is time related to gravity? And you might think they're not really related to each other. But I want to leave you maybe with this poser, with this puzzler. Like, first you have to answer, what is time? Like, we haven't even gotten into this, right? What is time? And I can say that it's not universally understood. There's little quips. Time is what prevents everything from happening all at once, et cetera. But that's not really satisfactory. The question of the actual nature of time, the connection of time to what's called entropy, the fact that we never see a cracked egg spontaneously going back into its shell and then reassembling, although the laws of physics don't preclude that from happening, that we don't see coffee mixed with cream dissociating into cream and coffee separately, even though that was their original state. That's something called entropy. Time connected to entropy. Is entropy connected to geometry of space itself? Why can't time come into existence? Why can't time be created from space? In other words, what if there were 4 dimensions of space, but no dimensions of time? I'm asking you, but you could ask me and I wouldn't have a better answer than you. But Hawking and his colleague Jim Hartle, who's up at UC Santa Barbara, they have these really interesting ideas that we should talk about for how the cracking on the distortion of a space dimension can actually fragment and create time out of nothing. And therefore, time could have a creation owing its parents, so to speak, to the suicide of these spatial dimensions.
So like you're basically saying something can happen in space that creates entropy, and we measure time by essentially entropy, by how distorted things get.
Yes, and we use
they just
But at the beginning
that's like
of
almost
time,
a rule of time.
Yeah. So then the question is, entropy always increases. You've probably heard that before. That entropy increases, just like the coffee cup. There's many more states for a coffee molecule to be intermixed with a cream molecule than there is. There's only one state where they're completely separate, right? There's a state where there's pure cream and pure coffee. Imagine half the cup. You're looking from above. The left half is all coffee. The right half is all cream. That's only one state. It's completely implausible. But there's an infinite number of states where there's like 62,500 million coffee molecules, 65,252, whatever, mixed together. There's many more states where they're mixed together with what's called high entropy. There's only one state with perfect order, which is called low entropy. There's a big question, though. How did the universe begin? How did it know to begin with low entropy so that later on it could evolve to having high entropy, so that we could use entropy as a type of clock to measure the elapsed amount of events that have taken place throughout all of space and time? It's a very good question. And what's cute about it is that we're going to come upon 2 different cosmological models, and I'm going to break them down. One is called a bridge model, and one's called a tunnel model.
And they both were going to nightclubs.
That's right. Yeah,
in Manhattan.
It's a small price to pay to get out of New Jersey. I'm sorry, James. I know you're from New Jersey.
Right. I was a bridge and tunnel.
You were.
kid,
That's right.
Except I never went to clubs. I was just stayed at home. But okay, so obviously we're going to have a part 2, maybe even a part 3. We'll see. We talked about the steady state, quasi steady state, Big Bang theory, although we're not quite done with Big Bang, I have a feeling. Nope. And then, of course, we briefly mentioned that we're going to talk about digital simulations. Yep. We'll talk about string theory. We're going to talk about, I've been doing all my research. We're going to talk about gravity rainbows. We're going to talk about
Bible. How about the Bible?
We'll talk about the Bible, and actually Orthodox Jews do have a way of unifying all of this. But we'll talk about quantum graviton fluids. Yep. We'll talk about 9 dimensions in string theory and how 3D universes collide, maybe how you just said.
A+.
Mirrored universes. Yep. We've got a lot of stuff to cover, and it's all going to make our lives better understanding this.
Can't wait. Yes, part 2 to infinity. From here to infinity.
Yes. Thanks so much, Dr. Keating.
Thank you, Dr. Altucher. I look forward to our next episode.
Twitter doctor on Twitter.
Epidemiologist and cosmologist.
At FedEx Office, we're here with the holiday cheer and expertise to help get your small business's to-do list done. Let us help you slay the holidays with the products, services, tools, and timelines that will make your business bright. Create more happy for the holidays at office.fedex.com.